We've already looked at how to graph functions that are transformations of sine and cosine. We will now look at how we graph functions that are transformations of the other four trigonometric functions: tangent, cotangent, secant, and cosecant. We're going to start with secant and cosecant because graphing those is actually best accomplished by graphing the corresponding function involving sine or cosine, which we've already seen how to do. So, for example, let's look at graphing the function cosecant of 2x plus pi. To do this, we're going to use the following. We're going to write cosecant of 2x plus pi as the reciprocal of sine 2x plus pi. So cosecant of 2x plus pi is 1 over sine of 2x plus pi. Now we can graph sine 2x plus pi and use that to graph out what cosecant looks like. So let's graph sine 2x plus pi. We know that the amplitude of this function is going to be 1, because that's based on the a in front of the sine, which we don't have any of. So the amplitude is 1. The period we can obtain by taking 2 pi and dividing it by b, the coefficient of x. So that's going to be pi here. And then the phase shift is negative c over b, which is negative, in this case, c is pi, and b is 2. We can also do the following. One thing that's often helpful is to take the expression that's inside your trigonometric function and place it inside an interval containing a standard period, one full period of sine. So we know sine goes on its standard movement of 0 to 1 to 0 to -1 back to 0 over the interval from 0 to 2 pi. And so we can solve this inequality, 0 less than or equal to 2x plus pi is less than or equal to 2 pi. To get that the same is going to happen as x in our problem goes from -pi/2 to pi/2. So that's what a single period of sine 2x plus pi is going to lie on top of, the interval from -pi/2 to pi/2. So let's look at how that goes. We have an amplitude of 1, so we're going to go up to 1 and down to -1. And a single period of sine goes from -pi/2 to pi/2. And of course, we want to make sure that interval gets split up into 4 pieces. So we get -pi/4, 0, and pi/4 as important points. So we know that the graph of sine accomplishes its standard movement from 0 to 1 to 0 to -1 back up to 0 within a single interval from -pi/2 to pi/2. And we can continue. We can keep counting up by pi/4s. Let's see, that'd be 5 pi/4, 3 pi/2, and continue graphing sine this way. And of course, it keeps continuing on. So this is what sine of 2x plus pi looks like. Now, cosecant of 2x plus pi is the reciprocal of this. And so, first of all, we want to identify where the asymptotes are. So the asymptotes will appear wherever sine takes the value 0, because cosecant of one of those points would be 1 over 0, which is undefined. So I'll give my asymptotes in yellow, and the asymptotes of cosecant are going to be where the yellow lines are, and I'll fix those locations in a second. So first of all, this is where the asymptotes of cosecant are going to be. Next, we'll graph out what cosecant actually looks like. So what we want to do is we want to take the peaks and the valleys, the highest and lowest points on the graph of sine, and use those to construct cosecant. Cosecant is going to come down, just barely touch the graph of sine at the peak or the valley, and then go back down like this. So we get that this red graph here is the graph of cosecant 2x plus pi. So that's how we handle things, and that's pretty much all there is to do about things when there isn't a number in front of the cosecant. So notice that we had an invisible 1 sitting here in front of the cosecant, and when that happens, this is all that you need to do. When there is some number in front of cosecant, then you're going to want to do something else, or rather, you're going to need another step. So let's look at an example of that. Let's graph 2 times cosecant of 3x. We'll make part of this a little simpler. Actually, instead of cosecant, we'll go ahead and go with secant of 3x to see that most of this goes just the same way. So step 1 is going to be to graph just secant of 3x. So step 1 is graph the function without that constant in front. And remember that secant of 3x is 1 over cosine of 3x. So the first step in step 1 is to graph cosine of 3x. So let's look at what we can say about cosine of 3x. Again, it has amplitude 1. It has period of 2 pi over 3. And it has a phase shift of 0. So what the phase shift of 0 means is that this function, the graph of cosine 3x, looks like the graph of cosine, and it's been compressed because the period has come down, but it hasn't been shifted back and forth at all. So in particular, that means that we know that cosine is going to start up here at 1 and go through its standard period, going from 1 down to 0 to -1 to 0 back to 1 on this graph over a period of 2 pi over 3. So let's see what that looks like. 2 pi over 3, half of that would be pi over 3, half of that is pi over 6, and then let's see, pi over 6, 2 pi over 6, which is pi over 3, then 3 pi over 6 would be pi over 2. So we have that the graph of cosine is going to look like this, because a single period of cosine forms this pattern where we start up on top, come down, hit the bottom, then come back up. And of course, we want to get the behavior of the graph on the other side of the line as well. These are all negative. And so here's what cosine looks like going to the left. It's going to continue. It's going to continue here. And once again, to graph secant, once we've graphed cosine, we're going to put asymptotes down where cosine equals 0, because the graph of secant is going to have an asymptote wherever the graph of cosine reaches the x-axis, because that's where cosine is 0. And again, we're going to want to graph out what secant 3x looks like by bringing a horseshoe shape down that barely matches or barely touches the graph of cosine right at the peak and the valley. So here's y equals secant 3x. However, the problem didn't actually ask for the graph of secant 3x. It asked for the graph of 2 secant 3x. And so here's where we can just use our standard knowledge of how transformations of functions works. And remember that when we take the function and multiply it by a number on the outside, that stretches the whole function vertically. Or in other words, it takes every y coordinate of the graph and multiplies it by 2. So if we take this red graph and stretch it out vertically by a factor of 2, it's going to look like this. Remember, we're stretching out from the x-axis, and so every point on the green line, which is y equals 2 secant 3x, is going to be twice as far away from the x-axis as the red line was. So in particular, we've got a few points we can note. We've got the point 0, 2, 2 pi over 3, 2, pi over 3, negative 2, and so forth. And this is how we can graph a secant or cosecant function that involves a coefficient in front. Notice that if the coefficient in front was negative, not only would we be stretching or compressing the graph, but we'd be flipping it over the x-axis. So if this were a negative 2 times secant 3x, then the green horseshoe in the middle of the graph would actually be pointing down, and the next ones would be pointing up, and so forth and so on. So let me finish what I was writing down. Step 1, graph secant 3x, and then step 2 is to stretch, compress, or flip the graph to get, well, in this case, 2 secant 3x. And this will apply whenever you have some non-zero a in the front of your function here. One thing that graphing out these trigonometric functions is really helpful for is determining the range of these functions, which is not always easy to see without graphing things out. So for example, this problem might have asked not only for you to graph this, but to find its range. So the first step is to graph it out the way that we have done. And then for the range, we want to look at all of the y values that are hit by some point on the graph of 2 secant 3x. So we can start with the upper components. These horseshoes up here, these are all copies of each other that are just repeating over and over again every 2 pi over 3 numbers, because that's the period of the function. And we can see that this horseshoe, the middle horseshoe, has a minimum y value of 2. That's the lowest point that this green horseshoe reaches vertically. And then it includes all the numbers greater than it. So part of the range of this function is going to be the set of all numbers from 2 to infinity, including 2, because 2 is in the range of this function. And similarly, if we look at the horseshoes down at the bottom, we can see that the range is going to include all numbers below and including -2. So the range for this function is going to be a union of 2 intervals, the interval from -infinity to 2 and the interval from 2 to infinity. So these are some questions that you will occasionally run into when you're looking at graphs of secant or cosecant. The ranges of sine and cosine functions are a little easier to describe, but again, using the graph is a very good way of doing that, and a good way of checking their work. All right, so that's pretty much all there is to say about graphing secant and cosecant. They are reciprocals of sine and cosine, and so most of the work to graphing them is the same as the work required to graph a transformed sine or cosine. Let's talk now about tangent and cotangent. All right, so let's see, how do we graph a function of the form a tangent bx plus c or a cotangent bx plus c? The first thing that we need to know here is what the basic graph of just tangent x looks like. And we saw this briefly before, but let's look at it again. So let's look at the graph of y equals tangent x. The thing to remember here is that tangent x is equal to sine x over cosine x, which means that tangent of x is undefined whenever cosine of x equals 0. So we know that cosine of x equals 0 when x equals, well, it certainly happens when x equals pi over 2, then 3 pi over 2, and 5 pi over 2, etc., but also negative pi over 2, negative 3 pi over 2, etc. And I'm getting all of this from just the unit circle, remembering that cosine corresponds to the x-coordinates of points on the unit circle, and therefore an angle of pi over 2, a quarter of the way around the circle, has a cosine of 0. Negative pi over 2, a quarter way around the circle in the other direction. Then 3 pi over 2, which is 3/4 of the way around the circle. 5 pi over 2, which is 1 1/4 of the way around the circle, so forth and so on. So cosine is equal to 0 at all of these points, at negative pi over 2, pi over 2, and what you get when you extend further along the x-axis in that pattern. So the first thing that we're going to want to do is we're going to want to note where those two asymptotes are. And I'm going to start with just the first asymptote to the left and the first asymptote to the right of 0. So I'm just going to start with these two before we move on to what happens next. Right, the other thing that I want to remember about how tangent works is that for a given angle, tangent of that angle is the slope of the line that the terminal side of that angle lies in. So if I have an angle whose terminal side is this green line, then tangent of that angle is going to be the slope of that line. Now, this helps us with a few things. For instance, we can see that tangent of 0 is going to be 0, and that's because if we look at the angle 0, which heads off directly to the right, the terminal side of that angle is horizontal, and the slope of a horizontal line is 0. So we can label the point 0, 0 on the graph of tangent. Next, we can look at what happens if we go halfway to vertical. If we go a distance of pi over 4, which is the same as 45 degrees, and is the angle that's exactly halfway between horizontal and vertical, we know that the slope of that line is 1. It has a slope of 1. For every 1 that it goes to the right, it goes 1 unit up. And so that gives us another point. Another useful point for us to label is the point pi over 4, 1. And similarly, if we go halfway to vertical in the other direction, then that angle has measure negative pi over 4, and that line has slope -1. Therefore, there's another point that we can label negative pi over 4, -1. So labeling these 3 points helps to graph out the graph of tangent. And then the other thing that we want to remember is that as the graph approaches the asymptotes, it's going to continue to get bigger and bigger and bigger, going off towards infinity as it approaches the asymptote on the right, and down towards negative infinity as it approaches the graph on the left. So that's what the graph of tangent looks like. Now, this is only one branch of the graph of tangent, and in fact, it's repeated. The period of tangent is pi, and this is where tangent is different from sine and cosine. Sine and cosine each have a period of 2 pi. Tangent has a period of pi. So the period of tangent x is pi, which is going to play into how we determine the periods for our translated functions here pretty soon. And as we shift pi to the right, we get another copy of the same graph, just pi further on to the right, and then another one that's pi to the left, and continuing on all the way to the right, all the way to the left, infinitely many branches that look like this. So this is what the graph of tangent looks like. And let's talk about how we translate this before talking about how we graph cotangent, which is going to be similar, but it's going to have a different graph that it starts with. So the thing that we want to remember is to remember the graph of this function, and in particular, you should remember these 3 points lie on the graph of tangent and these 2 asymptotes, and then remember that the graph repeats itself over and over again as you move to the right and the left. Okay, so let's see how we can graph out a translated form of this. So to graph y equals a tangent bx plus c, rather than building it up in a bunch of steps like we did last time, we can look at all of these together, because we can often do these at once. So let's start with the bx plus c, the stuff inside. We have that one period of tangent occurs in the interval from negative pi over 2 to pi over 2. So when the one period of tangent theta, I should say, occurs in the interval where theta, the inside expression, goes between negative pi over 2 and pi over 2. So one period of a tan bx plus c occurs in the interval defined by bx plus c lies between negative pi over 2 and pi over 2. So we can always take whatever's inside the tangent function, put it between negative pi over 2 and pi over 2, and use that to tell how the graph of our function is going to work. So working this out in general will let us determine the period and the phase shift for tangent. So let's start by subtracting c from all sides. And so we'll get negative pi over 2 minus c is less than or equal to bx is less than or equal to pi over 2 minus c, and then divided by b. This gives us that negative pi over 2b minus c over b is less than or equal to x is less than or equal to pi over 2b minus c over b. So one period of tangent, one branch of it going from negative infinity to positive infinity, occurs as x goes between the expression on the left, negative pi over 2b minus c over b, to the expression on the right, pi over 2b minus c over b. And in practice, these will be simplifiable, generally. But there are two things that we can see from this. First of all, the period is the difference between these two expressions. And so if we take their difference, we get pi over 2b minus c over b minus negative pi over 2b minus c over b. We are going to get pi over 2b plus pi over 2b, because the c over b expressions are going to cancel. And that's going to give us 2 pi over 2b, which is just pi over b. So this is the period of our tangent function. You'll notice that it has a similar formula to the period formula for sine and cosine, and secant and cosecant. Those functions had periods that were equal to 2 pi divided by b. And that was because the original functions had periods of 2 pi. The function tangent has a period of pi over b, and that's because the original function tangent has a period of pi. So to calculate the periods for tangent and cotangent functions, it's a slightly different formula than the formula for the sine, cosine, secant, and cosecant. Then the phase shift for tangent is actually the same negative c over b expression. This tells you, once you've changed the period based on the value of b, negative c over b tells you how far you shift the graph to the left or the right in order to get the graph of the whole function itself. So you'll notice that the formula for the phase shift is the same for tangent and for cotangent when we get there as for sine, cosine, secant, and cosecant. However, we don't have an amplitude per se. We don't tend to define amplitude for tangent and cotangent, and that's because these don't oscillate. they go from negative infinity up to positive infinity and then come back down, and they don't have boundaries. They don't go back and forth between two numbers, and so they don't have an amplitude per se. But we do use this value a to tell us how to multiply our y values. Let's do a couple of examples where we see how this goes. So let's graph y equals 3 tangent pi x minus pi over 4. So there are a few things that you might want to do here. The problem might ask you specifically for the period. Let's suppose that it does. The period of this function is given by pi over b. In this case, b is just pi again. So in this problem, this function has a period of 1. So that's how we that's where we start. I find that to graph these tangent functions, it's often better to start with the inequality that we were working with at the beginning of the discussion on the previous slide. We know that one branch of tangent normally occurs as x moves between negative pi over 2 and positive pi over 2. So we're going to take the whole function, that's the whole expression that's inside the function tangent, and set it between negative pi over 2 and pi over 2, and we're going to solve for x. The interval we get out of that will tell us what the interval is where our function tangent accomplishes one of its cycles. So let's add pi over 4 to both sides, and we'll get that negative pi over 4 is less than or equal to pi x is less than or equal to 3 pi over 4. Now we'll divide everything by pi to get x by itself, and get negative 1/4 is less than or equal to x is less than or equal to 3/4. That tells us that this function, it accomplishes one cycle on the interval from negative 1/4 to 3/4. In particular, this tells us that negative 1/4 and 3/4 are where we have asymptotes. Let's graph this out. We've got negative 1/4 and we have 3/4. And as always, we want to split this up into 4 pieces. So halfway in between negative 1/4 and 3/4 is 1/4. And then in between those is 0. And in between 1/4 and 3/4 is 1/2. We want to label these points. And then we want to label the asymptotes. Now, at this point, I recommend graphing out the function without the 3 in front. So let's just graph y equals tangent of pi x minus pi over 4. And the reason why you'd want to do that is because we can make it match up exactly with the graph that we're familiar with, just with different tick marks on the x-axis. So we know that in the middle of tangent's interval, where it accomplishes one of its periods, in the middle, tangent has the value 0. And then when you move to the right, you get a y value of 1, and when you move to the left, you get a y value of negative 1. And so this function is what the graph of y equals tangent of pi x minus pi over 4 looks like. And when you do this, when you graph out just the function without the number that multiplied in front and without the number that's added to the whole function, if you had one of those, we don't in this case, if you just look at tangent of whatever's inside it, the y values of the points that you're going to be graphing are always going to be 0, 1, and -1, and tangent's going to be moving up to the right like this, assuming that b is positive. So it's actually helpful to write down what the coordinates of these points are for the next stage. So the 3 points that we have on our graph are 1/2, 1, 1/4, 0, and 0, -1. So now we multiply the y values of these points by, in this case, 3. We multiply them by whatever the a value was of our function. And so we will get for our final answer, that one of the points in our answer is 1/2, 3. And then we'll get 1/4, 0, because 0 times 3 is still 0. And then we will get the point 0, -3. And in each of these cases, we've taken the point that we had on our blue graph and multiplied the y coordinate by 3. And once we do that, we can graph out what the graph of tangent is that goes through those. And in this case, the graph of 3 tangent pi x minus pi over 4 is very steep and goes up approximately like this. The last step is to duplicate this, because this is just one period of this tangent function, and there are going to be more of them. So there's going to be a bunch more as you move to the right and as you move to the left. And in order to figure out what the points on this graph are, so for instance where these points are, you can look at the period. The period is 1, which means that as we move from one period to the next, we've shifted to the right by exactly 1. So this point 1/4, 0, when we shift it 1 to the right, gives us the point 5/4, 0, and that's also on the graph of tangent, of the red function that we're graphing out. And similarly, we'd get -3/4, 0. Going from 1/2 and subtracting 1, we'd get -1/2, 3. And adding 1, we'd get 3/2, 3. And then from 0, -3, we would get 1, -3 on the right branch, and then -1, -3 on the left branch. So that's how we can graph out a complex tangent function. Now, if a were negative, then when you multiplied the y coordinates of these points by a, they would flip around to the other side of the x-axis. So while each of the branches of tangent are increasing, if your a value in front is negative, then each of the branches will be decreasing instead, because they're going down. Because everything's been flipped over the x-axis. Okay, so to work on cotangent, we're going to do essentially the same process, The difference is that we're going to start with a different graph. We're going to start with the graph of cotangent rather than the graph of tangent. So let's look at what that graph looks like. So let's look at the graph of y equals cotangent of x. And remember that cotangent is equal to cosine x over sine x. And this means that cotangent x has an asymptote wherever sine x equals 0. And that occurs when x is equal to 0, pi, 2 pi, etc., and then negative pi, negative 2 pi, etc., going the other way. So when x is a multiple of pi. And again, this comes from the unit circle. And the fact that the points corresponding to angles like 0, pi, 2 pi, etc., all have y values of 0, and sine comes from the y values. So we can start graphing our cotangent function this way by graphing the asymptotes. So we've got asymptotes at 0, at pi. Actually, let me back that up a little bit. At pi, at 2 pi, and I'll put another one over here at negative pi. So let's mark our asymptotes. Like this. And let's graph out some points. Now, cotangent is cosine over sine. Tangent is sine over cosine. And we saw that tangent can be interpreted as the slope of the line that the angle's terminal side lies on. Cotangent is the reciprocal of the slope of the line that the terminal side of the angle lies on, which is not as familiar to us. So rather than doing that, I want to move forward, and let's be optimistic that it'll make sense to write things down in 4 parts like we have been, that in between 2 asymptotes, the point in between, exactly halfway between, should be important, and then the points that split the whole interval into fourths should be important, just like it was for tangent. And let's work out what cotangent of each of these numbers are. So cotangent of, let's do the middle one first. Cotangent pi over 2 is cosine of pi over 2 over sine of pi over 2. Now, cosine pi over 2 is 0, and sine pi over 2 is 1. So that tells us that cotangent of pi over 2 is equal to 0. So this is the point pi over 2, comma 0. All right, next we have cotangent of pi over 4. Now, this we can figure out using one of our standard triangles. The pi over 4, pi over 4, pi over 2 right triangle looks like this. 1, 1, square root of 2. Which means that cotangent of pi over 4 is, well, we can work it out as cosine over sine again, but we can also just work it out using its ratio, that it's adjacent over opposite. The adjacent side is 1, and the opposite side is 1. So that means that cotangent of pi over 4 is 1, because it's the ratio of 2 equal sides. So we have the point pi over 4, comma 1 on the graph of cotangent. And then if we have cotangent of 3 pi over 4, well, for this one, we'd want to work out the triangle over here on the unit circle, or on the graph. So if we've got the angle 3 pi over 4, that has a reference angle of pi over 4. So the triangle that's being constructed here on the graph is a 1, 1 square root of 2 triangle, except we need to label the horizontal side -1 because it's going to the left. And therefore, cotangent of 3 pi over 4 is the adjacent side over the opposite side. The adjacent is -1, the opposite side has length 1, and therefore we get -1 out of it. So the third point that we use to graph cotangent is 3 pi over 4, comma, -1. From there, cotangent looks similar to tangent, except you'll notice that it's decreasing, and it's got its asymptotes in different places. So it has a lot of similarities with tangent, but some differences you need to be aware of. So what this means for us that we want to work out. First of all, we can see that the period of cotangent is pi, just like for tangent. Also, cotangent does one complete period in the interval between 0 and pi. So we're going to use that to graph out cotangent of transformed versions of cotangent when we go to do that. So it does one complete period in the interval from 0 to pi. It has 3 points that we're going to want to mention that occur at the middle of the period and 1/4 of the way through and 3/4 of the way through. And the y values of those points are 1, 0, and then -1. So we're going to graph cotangent similarly to how we graphed tangent. So let's see how this goes. So let's graph -1/2 cotangent of 2x plus pi over 2. And again, let's suppose that the problem asked you for the period. In this case, the period has the same formula as for tangent. It's pi over b because the period of cotangent is pi, so that's pi over 2. To actually graph out cotangent, the easiest way to do that is, again, to take 2 pi plus pi over 2 and put it in the interval where we know cotangent makes one complete period. And we know cotangent does that on the interval from 0 to pi. So remember, this is a different interval than we used for tangent. For tangent, we use the interval from -pi over 2 to pi over 2 because that's where the asymptotes were. For cotangent, we're going to use 0 to pi because that's where the asymptotes are. So we'll subtract pi over 2 from both sides and get -pi over 2 is less than or equal to 2x is less than or equal to pi over 2. Then we'll divide everything by 2 and get that -pi over 4 is less than or equal to x is less than or equal to pi over 4. So in this case, we have that cotangent, this cotangent function, is going to complete one of its normal cycles between -pi over 4 and +pi over 4. So again, we'll start by putting in the asymptotes. and putting in our tick marks. We want to split it in half, and in this case, this interval happens to be centered around the origin, so 0 is the halfway point here. And then we want to give our halfway points here, which in this case will be negative pi over 8, and then pi over 8, because those are the halfway points in between the origin and the two asymptotes. Now, once again, we're going to want to start by graphing y equals just cotangent 2x plus pi over 2. We're going to use the points that we know show up on the graph of cotangent in the order we know they show up in, and then after we graph that, we'll adjust the y values based on this coefficient in front of our problem. So we know that cotangent is decreasing, and we know that a quarter of the way through its period, it has value 1, halfway through its period, it has value 0, and 3/4 of the way through its period, it has value -1. So that tells us that cotangent of 2x plus pi over 2 looks approximately like this. And we can even graph out or label these points, which is a very good idea. And now to graph cotangent itself, or sorry, the function itself that we were looking at, y equals -1/2 times this function, we're going to take all the y values of the points that we've mentioned and multiply them by -1/2. So y equals -1/2 cotangent 2x plus pi over 2. So we're going to keep the x values the same on each of them, just multiply the y value by -1/2. So our point -pi over 8, 1 becomes the point -pi over 8, comma, -1/2. The point 0, 0 stays where it is, it's still 0, 0. And then the point pi over 8, comma, -1 becomes the point pi over 8, comma, +1/2, as we multiply by -1. And so now we see that the points of our final function, our red points, fall into this pattern here. So the graph of -1/2 cotangent of 2x plus pi over 2 looks like this red graph. You'll notice that this is increasing rather than decreasing, and that's because our coefficient in front of the whole function was negative. It switched it from being decreasing to increasing. To finish up, we can graph out a couple more cycles of this. I want to start with the asymptotes. And remember, we can find the locations of these by shifting over by the period. The period of this graph is pi over 2. And so to find the x-coordinate of the rightmost asymptote I've drawn, I can take pi over 4 for the previous asymptote and add pi over 2 to it. Pi over 4 plus pi over 2 is 3 pi over 4. So that's pi over 4 plus pi over 2, which is the period. And I can subtract pi over 2 from -pi over 4 to get -3 pi over 4. And then I can similarly shift all the points on the graph over by pi over 2 to get the graph of the rest of the graph of cotangent. So this is the strategy for graphing secant, cosecant, tangent, and cotangent. It follows a lot of the same strategies as for sine and cosine. You just need to know what the original graphs look like in order to know how to transform them in the proper way.